Hi, my name is Shahnawaz. In this lecture, we will discuss the metric topology. The metric topology is the most important and frequently used ways of imposing a topology on a set. But before we discuss the metric topology, we'll first define uh, what do we mean by a metric. So we have this definition here. So a metric on a set X is actually a function. This is a function, a real valued function, say d from the Cartesian product of x with x to r, having the following properties. The first one is that this the function d is non-negative, i.e. d of xy is always non-negative for all x and y in x, and the equality holds here only when x is equal to y. Equality holds if and only if this x is equal to y. The second condition is of symmetry, that is d of xy is same as d of yx. This is also true for all x and y in x. And finally we have the triangle inequality, that is d of xy is always less or equal to d of say xz plus d of zy for all x, y, and z in x. Now, uh, so given a metric d on x, the number d of dxy is often called the distance between x and y in the metric d. So here it is clear that the distance between 2 points may be either 0 or it is positive, and it is 0 only when these 2 points coincide. And if we measure the distance from the point x to y, it is same as the distance from the point y to x. And if we have 3 points, say x, y, z, say this is x, this is y, and this is point z here, then this distance xy, this is less or equal to less or equal to the distance from x to z plus from z to y. So in this case it is strictly less than. However, if this z lies here, then distance from x to y is same as distance from x to z plus z to y. Now given, suppose given any epsilon positive, so given any epsilon bigger than 0, consider the set so we have this set here bd, say x epsilon, which is the set of all points in x whose distance from I mean the set of all points y in x whose distance from x is strictly less than epsilon. So this is a set of all pointers in X whose distance from X is less than epsilon. So this set is called the epsilon ball centered at X. So if we have this space here, this is the set X here, and we have some points, say this little x here. Now consider all the pointers y in X which are at a distance of uh, at most y from at most epsilon from this point X. So if this is the distance, I mean y and distance epsilon here, then we pick all the pointers which lie in this bounded region. So one can note here we had the strict inequality here. So that is why we exclude this boundary, because this is the distance epsilon. So apart from these points which are on the boundary, we pick the interior of this region, and this interior is over epsilon ball. So it is called the epsilon ball centered at X. So this X over here, this is a center, and this epsilon is the um, radius, and this d indicates the metric with respect to which we take this open ball. So sometimes we omit the metric d from the notation, and we write simply this ball as bx epsilon when there is no confusion of metric. However, if there are more than two metric involved, then we have to specify which I mean with respect to which metric we are taking this open ball. Now we have this result here. We have the proposition. So if D is a metric on the set X, then the collection of all epsilon balls uh, is a basis for a topology on X, and that topology is called the metric topology on X, induced by the metric. So if this little d is a metric on the set X, then the collection of all epsilon balls BD X epsilon for X in X, and this epsilon to be a positive real number. So this is a basis for a topology on X, and that topology is called the metric topology induced by D. Now let us prove this result over here. So we had the proof. So let us take, so let fancy be the collection of all balls. Say now here we know we had the metric d involved, so we'll omit the d from our notation. So this is the collection of all balls centered at x and any arbitrary radius epsilon. So x is in x and this epsilon is arbitrary. I mean, this is not fixed epsilon here. This epsilon is arbitrary. So we are we'll prove that this B forms a basis for some topology on X. Now to prove this B is a basis, we have to prove it satisfies the two conditions for being a basis. The condition one is that for each x in X, there must exist a basis element, say Bx epsilon, and the condition second is that if we have an element, say y, which is in the two basis elements, then there is a third basis element which contain that point, and that base element is contained in the intersection of the um, I mean the original basis elements. So this is our basis element. So condition first is trivial. So I mean, so so this fancy B clearly satisfies the first condition for a basis. The reason is that since for any x in X, since this is the collection of all balls centered at each point in X with any arbitrary radius, uh, then uh, for any x in X, there there exists a basis element. There exists some element b x epsilon in this fancy B such that x is in the basis element uh, b x epsilon. So this is trivial. The condition first is trivial. Now before we prove the second condition, we'll first prove that. So now let y be any element, y be uh, so now let y be any point uh, of the base element, say bx epsilon of the not base element, any point of the set b x epsilon. So we have a basis element, not base element, we have a set, we have an open ball, say bx epsilon. So this is the center x and this is the radius epsilon. Now let us pick some point y in this set. So we have a point, say y here. So this is the point y over here. Now what we do, we choose delta. So let delta be equal to epsilon minus the distance between x and y. So one can note here, this is the distance between x and y. So this over here, this is the d of xy, and this is the epsilon from x to this boundary. This is epsilon. Now what is delta? Delta is this epsilon minus this distance over here. Sorry, this distance, I mean, let us pick different color. So this is the distance between this red segment is the distance between x and y, and this blue line over here, so this is the distance, I mean, this is the epsilon. Now when we subtract this epsilon by the distance of x minus y, we are left with uh, this distance over here, this green one. So this green one is over delta. So delta is obviously positive because y is inside uh, the ball bx epsilon. So since d of xy is less than epsilon, epsilon minus d of xy will be bigger than 0, and hence epsilon minus d of xy, when this is bigger than 0, this implies this delta is positive. Now let us pick an open ball centered at y and radius delta. So let I mean, now consider uh, the open ball by delta. So we have this ball over here. This is centered at y and radius epsilon. Sorry, delta. Now we want to prove that this ball by delta is contained in the ball bx epsilon. Now to prove this, we pick any point here and show this point, and this point is also here. So let uh, x, let us call this z. Now let z belongs to by delta be any point. Then now since this z is inside this ball, therefore distance between y and z is strictly less than delta. Then distance between y and z is strictly less than delta, and hence by triangle inequality, so let us pick this z over here. So by triangle inequality, so we have this triangle here, this is y, this is x, this is z over here. Let us call this z. So by triangle inequality, distance between x and z is less or equal to distance between x and y plus distance between y and z. Distance between x and y plus distance between x and y and z. Now distance between x and y is same as delta minus epsilon minus delta. So which is less or equal to, so this number over here, so this can be obtained from here. So this is uh, epsilon minus delta, and distance between y and z is strictly less than delta. I'm sorry, delta. So this is equal to epsilon. That means distance between x and z is less than epsilon. So which is only true when z is in the open ball b epsilon, bx epsilon. So hence x is in the ball b x epsilon, not x, sorry, z. That means this ball is contained inside bx epsilon. So hence by delta is sitting inside bx epsilon. Now let us prove the second condition for this fancy b to be a basis. So now to prove uh, the second condition for a basis for fancy b to be a basis, what we do, we pick an element. So let um, y belong to the two base elements, say b x1 epsilon 1 intersection b x2 epsilon 2. So by is in the intersection of two elements. Now we have to show there is one more base element, I mean one more element from this fancy b which contains y and is contained in this intersection. So since this y is in this base element, then using this I mean what we proved here, using this thing over here, there is a delta positive and y1 such that the ball centered at y1 and radius delta 1 is inside the ball bx1 epsilon 1. So we just proved above, we just proved above that there exists delta 1, I mean the positive real numbers delta 1 and delta 2 such that the ball centered at y1 and radius delta 1 is inside the ball centered at x1 and radius epsilon 1, and the ball centered at y2 and radius delta 2 is inside the ball centered at x2 and epsilon 2. So let us make these two balls. So this is the ball bx1 epsilon 1. So this is the point x1, and let us pick another ball centered at x2, and this radius is epsilon 2, and here this radius is epsilon 1. Now we have the point this y, which is in the intersection of these two balls. So since we proved above, there is some delta 1 positive and delta 2 positive, such that um, the ball centered at this point is over here. So this is the ball b y2 delta 2, and this is the ball over here, the ball b y1 delta 1. So if we pick delta to be the minimum of now here, so it is not y1 y2, it is actually y in the both cases, because this y is in the ball b x1 epsilon 1 and b x2 epsilon 2. So take delta to be the minimum of delta 1 and delta 2, then the ball B centered at y and radius delta is inside the intersection of these two balls, which is the ball centered at x1 and radius epsilon 1, intersection the ball centered at x2 and intersection and the radius epsilon 2. So this proves the second condition for this fancy B to be a basis. Hence, this fancy B is a basis for some topology, say Tm on X, and that topology Tm is called the metric topology on X. So one can note here this topology is induced by the metric, because the open balls, I mean the open sets, I mean the elements in the basis are induced by the metric. They are formed by the metric. So that's basis for uh, some topology on X. Now we can rephrase the definition of the metric topology as follows. So let us call this a short lemma. So a set U is open in the metric topology induced by the metric, say D, if and only if for each y in U there is a delta positive such that the ball centered at y and radius delta, which is induced by the metric D, is inside U. So this is the another way to look at metric topology. I mean, this tells us how the open status in a metric topology look like. So in metric topology, we call U to be an open set if at each point in U we have uh, an open ball which entirely lies in U. So let us prove this. So let us first assume that U is an open set. So let U be an open set in I mean this is an open set in the space X. So let U be an open set. So since this fancy B, this is a basis for topology, hence the open sets in that topology are the unions of the elements of this script B. Since C U is open, so U has to be the union of some elements in this fancy B. So then B being the basis for the metric topology, U is the union of is the union of is I mean is some union of the elements in B, and hence for any y in U there exists a basis element, say B x epsilon, such that y is inside B x epsilon. So these are induced by the metric D. Now the using what we proved above, that means that is if we have a ball B x epsilon, then for any point y in this ball we have another ball centered at y and radius delta, where delta is the difference of epsilon and the distance between x and y. So using this uh, concept here, so for this y, um, so hence there exists a delta positive such that the ball centered at y and radius delta is contained in bx epsilon, where and this delta is actually epsilon minus the distance between x and y. So this proves this notion over here, i.e. for each y in U we have a ball by delta which contains y, and the ball is contained in this ball. So this proves one direction. Now conversely, um, suppose for each y, suppose for each y in y, sorry, each for each y in U there exists a delta positive such that by delta is contained inside U, then U is clearly the union of the open balls, and hence U is an open set. Then U is clearly the union of open balls, and hence U is an open set. Now let us give some examples here. So we have the example first. So consider the metric space. So consider the metric space xt, where x is assumed to be non-empty, and this d is the discrete metric, i.e. where d is the metric defined as, so d of xy defined as, like this. So this d of xy is either 1 or 0. It is 1 if these 2 points are not equal, and it is 0 otherwise, i.e. if x is y. Now let us look uh, the open balls which are induced by this metric. I mean, how the open balls will look like when this d is the discrete metric. Now let us consider the open ball BD XR. I mean the ball centered at X and radius R. So centered at X in X and radius R positive. So this R is any real number. Suppose this R is less or equal to 1. So suppose R is less or equal to 1. Then this BDXR is the set of all pointers. I mean, let us take this R to be equal to 1. So then BDR is a set of all pointers y in X whose distance from y is strictly less than 1. Now here the distances are either 1 or 0. Now if distance is strictly less than 1, then it has to be 0 because there are only two choices for the distance. So that is, it is a set of all points x and x such that distance between x and y is 0. Now distance of x and y is 0 if and only if x is equal to y. That means this set is the singleton x alone. That means this open ball induces this set. So this set has to be open. So if R is less than 1, then each singleton is an open set. That means the topology in this case will be the discrete topology. So hence in the topology, hence the topology induced by d on x is same as the discrete topology on x. Now we have one more example. So consider the metric space, uh, consider the metric space xt, not xd. Let us take this x to be the equivalent space, say R, and this d to be the standard metric, I mean the usual metric, where distance between x and y is the absolute value of x minus y. Then the topology induced by the metric d is this standard topology, i.e. the usual topology on R, because so then b x epsilon will be the set of all points in x such that distance of xy is less than epsilon. That is the set of all pointers. Let us make this concrete here. Let us take this point A. So we call this A. So this is the set of all pointers x in x such that distance between A and x is less than epsilon. So this is list of all points x in x such that mod of A minus x is less than epsilon. So this is same as the list of all points which lie in the interval A minus epsilon and A plus epsilon. So this is an open set with respect to the usual topology. So this standard metric induces this standard topology on X.